Rust began not in a corporate boardroom or a university lab, but in the mind of a single programmer frustrated with the limitations of existing languages. This is the untold story of how a personal project became one of the most loved programming languages in the world. In 2006, Graydon Hoare was working at Mozilla when he returned home one evening to find his apartment building's elevator broken. The culprit was a software crash. This incident crystallized a problem that had been bothering him for years. The languages used to write critical system software were fundamentally unsafe. Memory errors, data races, and undefined behavior plagued even the most carefully written code in languages like C and C++. Hoare began working on a new language in his spare time, initially calling it Rust after the rust fungi, organisms known for their resilience and ability to thrive in harsh conditions. His vision was ambitious: create a language that could match the performance of C and C++ while guaranteeing memory safety without requiring a garbage collector. Most experts considered this combination impossible. For 3 years, Rust remained Hoare's personal project. He experimented with different approaches to memory management, drawing inspiration from functional programming languages, the actor model, and research into type systems. The breakthrough came with the concept of ownership, a system where every piece of data has a single owner, and the compiler enforces strict rules about how that data can be accessed and modified. In 2009, Mozilla officially sponsored the project. The company had been struggling with memory safety issues in Firefox, their flagship web browser. Crashes and security vulnerabilities stemming from memory errors were constant problems. Mozilla saw in Rust a potential solution, not just for Firefox, but for the entire ecosystem of systems programming. The early years of Mozilla's involvement were marked by radical changes. The language went through numerous iterations, with features being added, removed, and redesigned. The team experimented with a complex system of pointers and regions, then simplified it. They added and later removed a runtime and green threading system. Each decision was driven by real-world testing and feedback from early adopters willing to work with an unstable, rapidly evolving language. One of the most significant innovations was the borrow checker, a compile time analysis tool that enforces Rust's ownership rules. The borrow checker examines code and ensures that references to data follow strict rules. You can have either one mutable reference or multiple immutable references to data, but never both simultaneously. This prevents data races at compile time, eliminating an entire class of bugs that plague concurrent programming. The path to stability was long and challenging. The language reached version 0.1 in January 2012, but it would be another 3 years before version 1.0 was released. During this period, the team made breaking changes with almost every release, frustrating early adopters, but ensuring the language's foundations were solid. Version 1.0 arrived in May 2015, accompanied by a crucial promise: backward compatibility. From that point forward, code written in Rust 1.0 would continue to compile with future versions of the compiler. This stability commitment was essential for convincing organizations to adopt Rust for production systems. The language's design philosophy centered on zero-cost abstractions, meaning that high-level features would compile down to code as efficient as handwritten, low-level code. Rust achieved this through aggressive compile time optimization and by moving as many checks as possible from runtime to compile time. The result was a language where safety did not come at the cost of performance. Rust's type system became one of its defining features. The language uses algebraic data types, pattern matching, and traits to enable expressive, safe code. Traits, similar to interfaces in other languages, allow for polymorphism without the overhead of virtual method calls in many cases. The option and result types force programmers to explicitly handle the absence of values and potential errors, eliminating null pointer exceptions and unchecked error conditions. The community that formed around Rust became as important as the language itself. The Rust team established a governance model based on working groups and request for comments processes, allowing community members to propose and discuss changes. The community developed a reputation for being welcoming and helpful, with extensive documentation and a focus on making the language accessible to newcomers, despite its complexity. Adoption began slowly but accelerated as the language matured. Dropbox rewrote critical components of their storage system in Rust, achieving better performance and reliability. Cloudflare used Rust for their edge computing platform. Microsoft began exploring Rust for systems components in Windows, publicly acknowledging that roughly 70% of their security vulnerabilities stemmed from memory safety issues that Rust could prevent. The creation of Servo, an experimental web browser engine written entirely in Rust, demonstrated the language's capabilities at scale. Components from Servo eventually made their way into Firefox, marking the first major deployment of Rust code in a widely used consumer application. Firefox Quantum, released in 2017, included Rust components that significantly improved performance. In 2020, the Rust Foundation was established with founding members, including Mozilla, Amazon Web Services, Google, Microsoft, and Huawei. This move ensured the language's future would not depend on any single company. Mozilla had laid off much of the Rust team earlier that year during pandemic-related restructuring, raising concerns about the language's future. The foundation provided stability and resources for continued development. Rust's influence extended beyond its direct usage. The language inspired features in other programming languages and renewed discussions about memory safety in the systems programming community. The United States National Security Agency and the Cybersecurity and Infrastructure Security Agency began recommending memory-safe languages like Rust for critical infrastructure, acknowledging the security implications of memory vulnerabilities. The language consistently ranked as the most loved programming language in developer surveys year after year, a testament to the experience of those who overcame its steep learning curve. Programmers appreciated the compiler's helpful error messages, which not only identified problems, but often suggested solutions. The tooling ecosystem, including the Cargo Package Manager and Build tool, set new standards for developer experience in systems programming. Rust found applications far beyond its original scope. It became popular for command line tools, web assembly applications, embedded systems, and even game development. The language's guarantees about memory safety and thread safety made it particularly attractive for concurrent and parallel programming, areas where traditional systems languages required extreme care and expertise. The story of Rust is ultimately about rethinking fundamental assumptions. For decades, the programming community accepted that systems programming required trading safety for performance, that memory management was inherently error-prone, and that preventing data races required runtime overhead. Rust demonstrated that these trade-offs were not inevitable, that careful language design could provide both safety and performance. From a personal project born out of frustration with a broken elevator to a language reshaping systems programming, Rust's journey reflects the power of addressing fundamental problems with innovative solutions. Its success lies not just in its technical achievements, but in proving that we can build more reliable, secure software without sacrificing the performance critical systems demand.